I also hate writing that symbol.
It's a really weird symbol.
Okay, so hopefully everybody had a good long weekend. Everybody got to 2.1. There's 45 seconds left on the clock for that quiz. We're going to round out chapter 1 and then start chapter 2. Okay, so there's a little bit at the end of chapter 1 about, okay, so if science is about measurements, that means numbers, and here is the proper use of numbers. And it gives us 2 words that we use all the time in English, but honestly don't really understand that well. And they're precision and accuracy. Precision is how much detail is in the recorded data. Okay? It's all about the level of detail. Accuracy is about how close the data is to the correct value. Okay? So these two, not the same thing. If we looked at the clock, here's the clock, and the little hand is pointing 3 almost, and the big hand somewhere between the 9 and the 10. And you ask, what time is it? You say, oh, it's 2:45. That's a valid answer that is acceptably precise and acceptably accurate, but it's not. We could all do better, right? We could do better than that, because we know that that hand is not right at the 9. If it were right at the 9, then it would be 2:45, then it really would be 2:45. You could, as equally, say, it's 2:50, and societally be as acceptable. It would be as precise and as accurate. But we can do better. What if there's a second hand? Here's a second hand. We could, if you're that kind of person, when you ask them what time it is, instead of saying, yeah, it's 2:45, they could say, all right, that is 2:47 and 38 seconds. That is both precise, well, that is precise, right? That's very, very precise. I've now got more detail. But then you look at your phone, and your phone says that it's 9:02 a.m. Okay, so somebody has given you a very, very precise answer that says that it was 2:47 and 37 seconds, but their answer is not what the correct time is. So if I ask you a question and you tell me your answer is close to the correct time, that it's almost 9:05, then your answer is accurate. If you tell me that it is 2:47 and 37, 2:47 and 37 seconds, then that is a precise answer.
Oh.
But what this clock is wrong. The real time is it's 5 minutes past 9. Okay, so that was a precise answer that is inaccurate. Accurate is how close are you to the correct value. Precision is how much detail do you have in your answer. Okay. So in making measurements, we have a little bit of scrutiny here. We know that the value is not 45 minutes, and we know that the value is not 50, and we're asked to invent another number that is somewhere in between, that is a good guess. And it appears to be more than 46 and less than 49. So 47 or 48 would appear to be good answers. And then we throw in a next guess about what this is. Okay. And that's the same thing as if you have liquid in a container, and this says it's 20 milliliters, and 10 milliliters, 20 milliliters, 30 milliliters, okay? Because you can read off the gradations on the flask. I know it's more than 20, and I know that it's less than 30. So if I, and those are the only two numbers right there that I have any confidence in, because the manufacturers put them on the glass. So what I do is I invent a best guess that goes in the middle. So the real definition of significant figures is you take the number that is given to you by whatever measurement device you have, and then you're allowed to invent one additional number after that. Okay, and that's going to end up being our significant figures, which are a measure of precision. They will not measure how accurate you are, because you can look at that clock and really measure where the second hand is. But if your clock is reading the wrong values, then it's inaccurate. It can be very precise, and still be inaccurate. Okay. So significant figures are the usable precision that are in numeric data. I just know usable. Is there an E in usable?
No.
No, there isn't. You're right. Significant figures is the usable precision in numeric data. And it's not that difficult, but if you've not seen it enough, it gets to be a little difficult to scan sometimes. Here's what we've got. Okay. I should have examples. I do. There's a quantity. 123.4 grams. All of these numbers are significant. Any real number, real numbers being, integers, something that is measured, and anything below the decimal point is a significant figure. So this contains all of those. That is 4 significant figures, because those are real numbers, and then we have a level of precision that is below. Okay. If my number was 0.035 liters. Now this number two, three, four, 5 digits in it. But those zeros don't count. Zeros before the first real number don't count. This right here has 2 significant figures. So the thing here I'm going to call that a real number. Real numbers in mathematics is something different, right? These, if you have a 0 before the first real number, they don't count. They don't count. So this value has 2 significant figures. If I did something like this and switched it up a bit and said 0.03, what have I got? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That 0 is in a different place. That is a 0 that is after the first real number. Therefore, it counts. This is 3 significant figures. So zeros after the first real number count because somebody recorded that number. Somebody recorded that number. Zeros before it, well, they just fall victim to your units. What if instead of reading this as liters, I read it as milliliters? What would 0.0035 liters be? What would that be in milliliters? Yeah, because there's a difference in 1,000. So you would multiply by 10, multiply by 100, multiply by 1,000. It would be 3.5 milliliters. But my answer just used to have 5 digits in it. Wasn't that 5 significant figures? No, because it depended on what your unit was. If you converted this into milliliters, it would be 3.5 milliliters, which tells you your underlying value only really has 2 digits of precision. Okay?
Let's say it was 3.0 liters. Would that be more than 2 significant?
3.0. Zero is after the first real number. Therefore it counts. That's 2 significant figures. Now there's this really dumb thing that they do in math that I absolutely detest. And they'll say, well, you take some number, blah, 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 so take some quantity right here, and I'm going to multiply it by 4, and sometimes they'll go 4 dot, which means it was only measured to 1 significant, like, that's the dot, and then you don't know any of the numbers after it. I don't like that. It's real, can't avoid it. We are going to avoid it, because I'm just not going to do it. Okay, so we hopefully can see. The only thing that's going to trick you out is the zeros. If the 0 is after a number, it's been measured as part of the number, and that counts as a significant figure. Now, this caught a couple of people out. I had questions about on the 1.2 quiz. You do slightly different things to the significant figures if you multiply a number versus if you add them. Slightly different. Okay. If I took a measurement Notice what should we do? If density is mass per volume, let's have a little bit of a callback. If density is mass per volume, we could, density is going to be quoted to 1, 2, 3, probably 3 significant figures, right? Let's do mass is density times volume. Okay. So here's a question. Here's an example. Gold bar has mass of 1, 2, 3, 4. You might need a calculator. 0.567 grams. And density of 19.3 grams per milliliter. What is the volume of that gold bar? Okay? So we know that D equals M over V, therefore M is D times V. Let's do that right from the beginning. So, I have volume. I set myself up to do a mass. So density is mass over volume, therefore volume is mass over density. Okay. Volume is the mass divided by the density. We're going to apply the same rule to multiplications and divisions. And that rule is your answer is only as good as your weakest amount of precision. So I've got this number. How many significant figures in that number? 7. Starts with a real number, and then has a decimal, and then numbers after the real numbers after the decimal. So that's all good. That's very, very precise. And then I looked up the density of gold at the back of the textbook, and it says 19.3. There's 3 significant figures. So let's put those numbers into our calculators. That volume is 1, 2, 3, 4, 5, 6, 7 grams divided by 19.3 grams per milliliter. And the grams divided by grams cancel, and then the per millimeter is going to right to the top and give me an answer that is in milliliters. So that looks to have worked. Someone with the calculator, tell me what your calculator test says.
63.96722021.
Calculator said it, it must be true. What the calculator says. And then here's what we're going to do to that number. And when you're doing your calculations, keep every value in. Write this number down first, because you know what's going to happen? After you've found volume, we're going to ask you to do something else to that volume, and then we're going to ask you to do something else to that number. Keep all of these units of precision in, and then round your number up to give the instructor the answer that they're waiting for. Don't round the numbers during the calculation. That leads to very, very poor quality. So, valid answer only contains the level of precision in the least precise measurement. Which is equal to, right, 7 significant figures here, and 3 significant figures there. So what I'm going to do is going to take that number and I'm going to cap it at 3. And it inadvertently has given us something else to talk about. So, if I cap that now, my answer says 63.9. But that 9, that 0.9 is closer, because this is a 6, is closer to being a 10 than it is being a 9. Because that next number is going to push that up. So the real answer gets to be 64.0. Yeah.
So how do you how is it like 63.9? Because like I know you got the answer, but how like did you like round it?
The weakest level of precision in my calculation, in my data that I used in my calculation, only contained 3 digits. That means my answer, I'm confident in my answer only to the first 3 digits. All of this other stuff that the calculator tells me, that's nice, but I can only be confident in the level of precision of this calculation based on the amount of precision that I put in. Okay. And then this ends up being 63.96, 96, round that up. I'm going to give you this value right here, and then again, don't forget to put the units in. A number without units is worthless.
What if we replace that 6 with a 4, and so would you, like basically if you're rounding up, because that 7 would cause the 4 to round up to a 5, and that would, basically, are you rounding up using all the numbers in the sequence, or are you just using the 6?
That's a really, really good question. So we're going to round that 9 up because it's followed by a 6. If it were a 5, we would also round it up. If it were a 4, we would round it down. If that 4 were followed by a 9, then wouldn't you round that 4 up to a 5? Yeah, at some point I'm going to just say no. Okay, and at some point you're now arguing detail that we don't have. If your level of roundingness is somewhere here, then it doesn't make any difference. It really doesn't. Okay, so that's the rule. For multiplying or dividing, your answer has the same number of significant figures as the least number of significant figures in the data. Slightly different when you add the numbers together. And this caused people who know how to use significant figures to get one of the questions wrong on the quiz. Because the rule for adding is slightly different than the rule for multiplying. Adding or subtracting data. Okay. Let's say I had this value. I'm measuring some, we're talking about gold, blocks of gold, and then finding the combined mass. I'm going to add these two numbers together. There's the decimal place right there. Okay, first thing to do, get your calculator out and add those two numbers together. And then we're going to decide where the significant figures kick in. Yeah. Add those two numbers together and it gives you, well, I'm going to guess that my first number is a 1, and that my second number is a 2, and that my third number is a 3, and I'm going to guess that my fourth number is a 4. And that my fifth number is an 8 point.
0, 1, 8.
Hello. So that's what your calculator tells you. Now, how many significant figures do we have in the top number? 1, 2, 3, 4, 5, 6, 7, 8, 9. The first number is a real number, therefore everything that follows it is significant. I have 9 digits of precision in my top number. How many digits of precision do I have in the bottom one? 3. First number's real, and then the numbers after it are real also. So how many digits of precision am I allowed in my answer?
3.
Would be the answer if you were multiplying those two numbers together. When you are adding numbers together, and here's why it's different. Somebody really measured all of those numbers. In order to be able to measure all of those numbers, they had to use a really precise instrument. Okay? Somebody also measured all of those numbers, but then it fell off. So my limitation, because I'm just adding these numbers together, not doing any fancy mathematical function, my limitation occurs here. That's where my confidence in my answer stops, at the second decimal. So when you're adding numbers together, you can only add them to the confidence of what decimal the smallest value has. What is the smallest decimal value? And here, there's the tens column, there's the hundreds column, here's the thousandths column. This one doesn't have one. Therefore, these numbers are now suspect. Because what number comes after this 4? Is it a, well, we don't know. Is it a 3? Is it a 2? Is it a 9? We don't know what that number is. Therefore, we cannot add it onto that number to tell us what happens next. I am allowed to round that 1/8 up to a 2. So my best answer right here is 1, 2, 3, 4, 8.02. Okay? So when you add or subtract number, your answer has the same number of decimal places as the least precise value Now, there is something else lurking here that we haven't seen yet. Conversion factors. Let's convert kilograms to grams. Let's say I had 1, 2, 3, 4, 5.67 kilograms of some compound that I'm interested in. I have this 1, 2, 3, so the first number is real. 1, 2, 3, 4, 5, 6, 7. I have 7 digits of precision. Okay? I'm going to convert that into grams. And I'm going to use a conversion factor. Now, what's the difference between kilograms and grams? It's 1,000. It's a factor of 1,000. So what we do, this is the very beginning of something that we call dimensional analysis. You write down the value and the units of the thing that you're using, and then you're going to write down the conversion factor. Now, because the kilograms are a numerator, they're above the line, here's what I'm going to do. 1 kilogram is equal to 1,000 grams. If I write the kilogram at the bottom, that value kilograms and this value of kilograms, they now cancel each other out. Gone. And my answer on the top line is now in grams. Put it in your calculator. So you get 1, 2, 3, 4, 5.67 times 1,000, and your answer comes out as 1, 2, 3, 4, 5, 6, 7, 0. Right? There you go. So 12,345,670 grams. Which number in your calculation is going to limit your significant figures?
Your conversion.
If I said this has 7 digits, and that has 4 digits, should I limit myself to the first 4 numbers right here? No, that would, I mean, that's just what we set ourselves up to do just a few minutes ago. If you're multiplying 2 numbers, the number with the smallest significant figures carries over into the answer. But somebody measured that to this level of precision. Why would you lose it just because you changed the units? Which tells us, where's my red pen? Conversion factors are exempt. They are not part of the significant figures discussion. Okay, so here's where it starts to get a little murky. How many significant figures are in my initial value? 7. How many are in my final value?
8.
How could it go up to 8? not allowed to do a mathematical function and improve the precision of my answer. It's not possible. What if I told you I had 1 kilogram? How many is that in grams? So 1 kilogram. How many significant figures do I have? Okay. 1 kilogram would be 1,000 grams. How many significant figures do I have? It's not 4. We haven't got to this part of the discussion yet. Zeros before the decimal don't count. Zeros after the first real number or after the decimal only count if there's another number after them.
Do they count if there's a decimal place in the?
Yes. So that's where that awkward decimal comes from. That's when we actually use it. So zeros after the first real number could be a consequence of us converting the units. This has 1 significant figure. Therefore, this only has 1 significant figure. Zeros after the first digit are not significant. Unless there is another number or decimal point. Oops. After that. Okay. So that one right there doesn't count. And then these 3 right here, they don't count. Mostly, it's kind of straightforward, and then occasionally it throws up something awkward like that. Okay, so let's do this. Here's a number. 12 million. How many significant figures are there? There's just 2. How many significant figures are there now? The decimal point starts to validate our numbers. Okay? You're allowed to have zeros as long as they're after a first real number. And then after the 0, somebody has measured those. That decimal point's real. Somebody has measured them. And then if there's a 1 there, oh, we're absolutely certain. Now, once you see another real number in here somewhere, you are absolutely certain. What about that? Don't know about that one. Because it's a 0 after a real number, after a decimal. So I start to worry about it. All right, moving on.
I'm confused. So the 12,000,000.000, those zeros after the decimal would count as significant figures.
The simpler version. They do this, and I told you I don't like it. Yeah. If there is a decimal, it validates the numbers that went before it, even if those numbers are zeros. Okay. Shouldn't have done the big number. matter that we're going to be measuring exists mostly in nature in the form of mixtures. A mixture is a combination of materials that don't interact chemically. And because, see, a chemical change would mean, or a chemical interaction would mean that what you put into your flask, your container, is not what you're going to get out of your container at the end of the day, because something's going on. So what this ultimately means is that mixtures can be separated. Into their components. Okay. Mixtures themselves exist in two major forms. They are heterogeneous mixtures in which the components are in different states. Which would mean something like a solid and a liquid. That's the typical one, where, you know, sand and water. Mud. Mud is a mixture. But you could separate the sand from the water really easily. You just put it on a big piece of cloth and let the water drain through it. It leaves the sand behind. Hey, you just filtered the solid away from the liquid. So, there you go. Homogeneous mixtures exist when the components are in the same state. And that could be two solids mixed together. I've got sand with glass in it. I've got sand with rocks in it. If you've got sand with glass in it, you can separate those. You could pick the glass out by hand. If you've got sand with rocks in it, what would you do? How do you separate those? You do what? Yeah, you shake it. You shake it and you let gravity have a go, and the sand falls through the cracks in the rocks to the bottom, and the rocks don't move anywhere, and they stay on the top. You've got glass in your sugar bowl. You can separate those. You dissolve the sugar. Glass doesn't dissolve. And then you dry the sugar out. Just let the water all evaporate. And you get your sugar back. And your glass is left over. You filter it out. It could be things that people don't think about that much. Liquids and liquids. Now, if you're a mixture, all it says is a combination of materials that don't interact chemically, but they're occupying the same space. A little bit of revisionist history right here. I had enough foresight to leave a gap for when I made a mental error. The components are occupying the same space. So when you have, here's a container, and it has oil on the top and water on the bottom, that's a mixture. Yes, there is a partition between the oil and the water, but they're occupying the same space. They're in the same container. and they can be siphoned off one from the other, therefore you can separate them. Gets a little bit more difficult when you start to throw gases into here, because gases are so independent of one another. There's so much space between the atoms that we're not really going to have much of a discussion with that. Okay. And then a note to yourself for much later, because there's an entire chapter on this. Not to ignore that they're there, but they exist. Solutions are a special case in which it's not a chemical interaction as such, although solvation can be considered as chemical under some conditions. It's really more of a physical thing. Solutions are a special case in which the components are no longer, oh, this is going to be awfully bad grammar. Visibly separable. Oof. That's translated from the original Greek. You mix salt and water. You know the salt's in the water, but you can't see it anymore because it's dissolved. We're going to do an entire chapter on solutions, so that's a special case. All right, other than being in mixtures, this leads us into chapter 2. Finally, some material is pure. Pure materials could be elements. Now, we have already mentioned, here's the periodic table, that most of the elements on this planet are metals, and many metals can be isolated and purified. And you have a block of gold or a block of copper or a block of iron, and that's all that there is in that block is pure material. This is elements, and an element contains only one kind of atom. The other thing that we can have that are pure are substances. And substances are combinations of atoms in fixed quantities. So salt is sodium chloride. And if we looked at a kilo of salt, we would find that for every one sodium that we could detect in our sample, there would be one equal chlorine. Fixed quantities that don't move. All right, that leads us up into chapter 2, which you've all read ahead because you did the pre-lecture quiz. We'll start 2 on Friday. We'll talk about the atom and all the good stuff that's inside it. It's a good time to start. Okay. See you Friday.